So let's go back to our garden variety t-test. Now we're testing a hypothesis about a linear combination of the regression coefficients and the vector that we're using to construct the linear combination of the coefficients, called L here. So L transpose beta minus 1 equals 0 is the null hypothesis. And by suitable choice of the elements in big L, we can test all kinds of hypotheses about linear combinations of the regression coefficients. And the alternate is that L transpose beta minus 1 is not 0. As before, our test statistic is going to be L transpose beta hat minus 1. That's a random variable. And the standard error of that random variable is going to be sigma hat squared, the square root of sigma hat squared times L transpose, open paren, X transpose omega inverse X, close paren inverse L. That's a scalar, because L was k by 1, so that L transpose is 1 by k. So we're pre-multiplying by something that's 1 by k, and we're post-multiplying by something that's k by 1, so we get a scalar, which is what we would expect, because L transpose beta minus 1 is a scalar random variable. Okay, so nothing really changed. There's nothing new, except that the coefficient covariance matrix is being measured on this new metric that we had to take account of when we distorted the shape of the distribution of the error term. Which brings us to the garden variety F test. Now we have a matrix, big R. R has, let's see, what are we, J rows in it. Big R has J rows and K columns. And J has to be strictly less than K. Why does J have to be strictly less than K as a dimension for big R? So you want the rank of R to be J. So we're going to impose J restrictions on the coefficient matrix, and the rank of big R has to be J, because if the rank is less than J, that means some of the restrictions are superfluous. But that doesn't quite answer the question that I asked. That's when you happen to be right in what you said, and you're a lot more right than telling me that your sweater is blue. Okay, so Van has given us some important information that goes beyond knowing that his sweater is blue, which means that the question that I started with goes to Frank, and he's going to tell us why J has to be strictly less than K. What are we in the business of doing as scholars, as researchers? Testing hypotheses. We're in the business of testing hypotheses, and how do we do that? Yeah, where do the test statistics come from? Yeah, we collect some data, and we construct some test statistics. In our garden variety regression model, don't we collect more rows of data than we have unknowns? So we always say, and we always require that the number of observations be at least as big as the number of unknowns, right? So hold that thought in your head. And now we're looking at this hypothesis, R, big R beta minus R is equal to 0, and I ask you, why does J...
We want some less restrictions than we have with the grades.
Yeah, otherwise we wouldn't have to bother collecting the data. We could just solve the system of restrictions to construct what the unknowns are. Okay, so if we know too much, we don't have to bother with collecting any data. If we knew that much, why not just go that route to begin with? Okay, so J is strictly less than K. Otherwise, we wouldn't bother with the whole experimental design and collecting data and running regressions and all the rest. We could just use our restrictions to tell us what the data's on. Okay, so J has to be strictly less than K. J is the number of rows, as Van told us. Big R has to be a full row rank, because if it's not, some of the restrictions that we impose are superfluous. So we're going to devise a new random vector that we'll call little q. Little q is equal to R beta hat minus little r, where little r is a vector of scalars that we pick, just like big R is a vector of numbers, that is a matrix of numbers that we pick. The beta hat is the random variable, and we've just assembled them as set of linear combinations in different ways. So now we have a new random variable called q, and under the null hypothesis, the expected value of q is 0, and the variance of q, since remember, all our tests of hypothesis require that we know something about the variance of our random variable. And so, do the lights just going up and down a little? They dimmed a little and then came back up. No? Maybe I must be feeling weak from lack of food or something. So the variance of q is the variance of R beta hat minus R. And by the way, this is a matrix, right? Because R has J rows in. This R beta hat minus R is a J by 1 vector. And so the variance of Q, the covariance of Q, is going to be J by J. So the variance of Q is sigma squared times R, X transpose omega inverse X, the quantity inverse, R transpose. Simple, if you think back to very basic statistics, when you were looking at the variance of a constant times a random variable, it was the constant squared times the variance of the random variable. Well, look what's happened here. You can think of if you had the variance of a times x, where x is a random variable, a is a scalar. That's a squared times the variance of x. Well, why not just say, you could have written it as a times the variance of x times a. So it's perfectly analogous to what we have here. So we've been assuming normality. So under the null, this new random variable that we invented has a normal distribution with a zero mean and the covariance matrix that we just derived. That said, I missed a j somewhere. I'm sorry. There are some characters missing. So if r beta hat minus r has a normal distribution, then the random vector q transpose times the metric on which it operates, all inverted, times q divided by sigma squared. That has a chi-square distribution with j degrees of freedom. So how are we going to build the f? Well, as it happens, so this has j degrees of freedom. And we know from the part that we already did that u transpose omega to the minus a half on that metric times omega to the minus a half u divided by sigma squared. That's also chi-square. And this time, it has n minus k degrees of freedom. So if we take those two chi-squares, the first one with j degrees of freedom and the second one with n minus k, we construct their ratio, divide the numerator and denominator by the respective degrees of freedom, we get an f. And the sigma squares cancel out. And probably the way you would be more accustomed to seeing it would be r beta hat minus r transpose r x transpose omega inverse x inverse r transpose all inverse r beta hat minus little r over j, where j is the number of restrictions, all divided by sigma hat squared, because the sum of squared residuals is already divided by n minus k, which is the degrees of freedom. Remember, sigma hat squared is y minus x beta hat transpose omega inverse y minus x beta hat over n minus k. Okay, so we have the ratio of two chi-squareds that have been divided by their respective number of degrees of freedom. So this is a perfectly general representation of what we have done a couple of weeks ago. Constable O'Clancy says, well, where'd you drop your key? I dropped it over there when I was coming out of the pub. Well, what are you doing looking here under the street lamp? Well, the light is better. Well, the same thing can happen in regression analysis. If the light is better, maybe we should look for the truth in a little different way. Suppose that there's a random variable x. There's a random variable x, that's its density function. And x has a mean. We don't know the mean u. We're trying to figure it out. And so we have an estimator that we'll call theta hat, which is an estimator for u. And there's g of theta hat. And the distribution of theta hat maybe has a really strange construction. That's the distribution of theta hat. And although theta hat has a weird shape, we know that the expected value of theta hat is mu. So theta hat is our unbiased estimator. Well, suppose that we knew quite a bit. We didn't know exactly what mu was, but we knew, what's the expected value of theta hat? Suppose we knew an interval in which mu fell. An example would be, what are the, according to John Maynard Keynes, what would be the allowable values for the marginal propensity to consume? Nobody talks about John Maynard Keynes anymore. No. The marginal propensity to consume is the marginal effect on consumption of a $1 increase in income. So if your income goes up, you spend more money. It's got to be between 0 and 1. Okay? Except in America, where because the Chinese are so willing to lend us more money, our marginal propensity to consume is bigger than 1. Because they, until recently anyway, they were really eager to lend us back all those dollars that we were spending there. So the marginal propensity to consume is supposed to be between 0 and 1. So that's an inclination. Which do you suppose has the bigger variance? Theta hat, which is unrestricted, or theta star, which is restricted to be between 0 and 1, which has the smaller variance? The restricted estimator, right? Because the restricted estimator, suppose that I impose a restriction on theta hat. I say I'm not going to allow theta hat to take a value smaller than theta L or bigger than theta U. So what I've done is I've taken all the probability mass in the lower tail and piled it up right here at theta L. And I've taken all the probability mass above theta U and I piled it up at theta U. And so the variance of the restricted estimator is going to be smaller than the variance of the unrestricted estimator. But suppose that I got the restrictions wrong. Okay, so let's make so theta hat is unrestricted, and theta star is a restricted estimator. So the only realizations of the estimator that I'm willing to accept are ones that fall between theta L and theta U. I get a smaller, theta star has a smaller variance than theta hat. But suppose I get the restrictions wrong. Suppose that Americans really have figured out a way to have a marginal propensity to consume bigger than one. Right? It seems like they have. The rest of the world is so worried about what's going to happen if they don't bail out America that they're all ready to lend us more money. So it looks like for the moment that we figured out a way to have a marginal consumer greater than one. Well, if I got the restrictions wrong, is theta star going to be unbiased? No, it can't be. The only way theta star can be unbiased is if I've got the restriction correct. So, for example, suppose instead of writing the restriction as between 0 and 1, I had said I'm going to restrict the marginal propensity to consume to be between 0.85 and 0.95. Well, more than likely that's wrong, with the consequence that my restricted estimator is not going to be unbiased. So apparently, there can be a trade-off between variance of your estimator and biasness. So that's what is happening here. We might be like Sean. We might be ready to look around for our lost key under the street lamp, knowing that it's wrong, but the search is going to be much smaller. So we can construct a biased estimator by imposing these restrictions and get a much smaller variance in return. And as long as we can tell which direction the bias goes, we might be well off. Right? So that's the idea behind this mean square error test. By definition, mean square error is equal to the variance plus the square of the bias. Because, where does that come from? Suppose we have an estimator that we'll call beta tilde, and our definition of variance is the expected value of beta tilde minus its expected value, post-multiplied by beta tilde minus its expected value. However, suppose we looked at beta tilde minus beta transpose. But suppose beta tilde is not equal to the truth. So now we want to talk about what our estimator is up to. So one of the things that we can do is, let's call this the mean square error. This is the error between our guess and the truth. Here in parentheses we have the difference between our guess and the expected value of our guess, which might be wrong. So instead, since we don't know whether or not we're right, we'll compare our guess with the truth. And then what we're going to do is we're going to insert beta tilde. We're going to add in the expected value of beta tilde and then take it back out again. Right? I can always add 0 and not change anything. And now what I'll do is let me regroup some things. So I'll regroup the piece that looks like that and group the other part. This piece is the bias of my estimator, the difference between the truth and the expected value of my estimator. This piece is what I have previously used in constructing the variance. So if I expand the square, when I expand the square, what I end up with is the expected value of beta hat minus the expected value of beta, these are tildes, sorry, tilde, beta tilde minus the expected value of beta tilde transpose, plus, and the cross between this piece and this piece vanishes. And you could do that on your own. Plus the expected value of beta tilde minus beta times the expected value of beta tilde minus beta transpose. So this is the square of the bias, the difference between the mean of my estimator and the truth squared. And this is just the variance of my estimator. So the mean square error has two parts to it. So if I'm willing to accept a little bit of a mistake, remember an F-test is predicated on the notion that the null hypothesis is exactly true. Right? Let me repeat because it's important. The garden variety F-test is predicated on the notion that the null hypothesis is exactly true. But suppose I'm willing to accept the proposition that the null hypothesis is only approximately true. In this sense, suppose in return for getting a little smaller variance, I'm willing to accept a little bit of bias. Why not construct a test statistic based on that idea?